Here we go. Example 5. So we're going to be given this T matrix. So T is given by this matrix here. To find the scalars x such that this equation, right, holds. So we have T times zeta, which is equal to x times zeta for non-zero eigenvectors zeta. What we're going to do is we're going to bring everything to the left-hand side. So we're going to take this equation and we're going to write it like this. Okay, so we're going to move everything over and we're going to write this as t zeta minus x times zeta. So we get this. And then what we're going to do is we're going to factor out the z vector and we're going to write it like this. Right, so we get t minus x times I, the identity, right? Because we're just going to get the identity here, times zeta equals the zero vector. Okay, so we can then, it becomes this. And so all I did was here, when we factor it out, and we get this, all we're doing is we're taking t minus x times the identity, which is going to put x's down the diagonal. And so when we subtract the two matrices, all we're going to do is get 1 minus x, 0 minus x, 3 minus x, which is what we have here. Everything else stays the same. Then we're going to get our zero vector here equal to this. And now we've got this system, right? So now this has this. Oh, by the way, this is a homogeneous system, right? So this linear system has a non-zero solution, which is the z vector here. Okay. If and only if the matrix is singular. So now here's the thing, we can determine that when that happens by looking at the determinant. So we can look at the determinant by saying, okay, well then when is, so we're going to take the determinant of this thing, showing, okay, when is that equal to 0? When is the determinant of this equal to 0? So that's what we're going to do. So we take the determinant of this. I'll just write this out. Okay. And of course, I'm going to let you figure that out, right? So we know how to find the determinant of this thing. So now all you have to do is apply the formula for finding the determinant of a 3 by 3 matrix, right? And simplify it, and you'll find that we'll get this equation. So we'll get this polynomial x cubed minus 4x squared plus 4x is equal to 0. So now we've got this cubic, right? Cubic polynomial. And we can factor this out, right? Again, something easy. We factor out the x, we factor out the x, and then we can factor out the quadratic, and what we end up with is this x times 2 minus x squared, or excuse me, the other way around. And so now the eigenvalues are lambda 1 is equal to 0. and lambda 2 is equal to 2. So there are the eigenvalues. To find the associated eigenvectors, plug in each eigenvalue. So now let's do that. So we got, let's do 0. So we get 1 minus 0, 2, 1, 2, 0 minus 0, negative 2, negative 1, 2, 3 minus 0. Okay? Times z1, z2 and z3 equals. Okay, so now all we have to do is solve. And when we solve this, we get that. And A must be non-zero because eigenvectors are defined to be a non-zero vector. Okay, so remember that. It's got to be a non-zero vector. Okay, so now let's do the same thing. Now let's plug in the other one. Okay, so what happens if we plug in the other one? We plug in 2, right? So if we plug in 2, what do we get? Again, we're going to get another system that we'll solve, and then we'll get another associated eigenvector. And so what we get is this. And again, I'm going to leave the solutions to proving that. And I would suggest, again, it'd be good practice to actually do the work and show that this gives you this. Okay, it'd be good practice. You should all, by this time, know how to solve this. Okay, using all the techniques and that we've learned. Okay, so again, prove it to yourself. Because again, you'll have to do it on an exam or the homework. So again, just practice makes improvement. All right. Have a great day.